And it's my great pleasure to introduce the next speaker, Professor Abhishek Dhar, International Center for Theoretical Sciences, Bangalore. Please, Professor Dhar.
Hi. So I'll start by thanking the organizers, Anton and Vitaly and others for this very kind invitation. So I think last time when we had met, we were hoping that it would be possible to visit St. Petersburg this year, and but unfortunately things have still not improved. Okay, so this talk that what I'll talk about today is a bit different than anomalous transport, but actually it's very closely related, and I hope it will really fit in with what was actually expected for of me to talk about. So this work is it's Newton to Euler and Navier-Stokes-Fourier. So the basic idea is to connect Newtonian dynamics and hydrodynamics, which are two ways of describing macroscopic systems. So this is work done with postdoc Shubhadeep Chakravarti, a student Santosh Ganappa, and a colleague at Boston, Paul Krapivsky. So Paul is of course from Russia, and he told me that I should St. Petersburg is one of the most beautiful and romantic places, and I should definitely go there sometime. So okay, so this is the basic outline of the talk. So the basic idea is there's the microscopic or Newtonian description of matter, and macroscopic description, which for equilibrium systems it's thermodynamics, but for systems in motion it's hydrodynamic description. And we want to check we believe the microscopic description is the really true description, but then how accurate is the hydrodynamic description? So this is what we want to test in a simple model. And the problem we study is something called the blast wave problem. So the blast wave problem, it's the basic idea is that you have a very hot region. So it's basically a bomb blast. And then it's expanding into a cold environment, right? So the question is, how does this expansion occur? So you can see it's a problem of, in some sense, of heat conduction, but then you have to worry about, there's a velocity field and there's a density field. You have to worry about all the hydrodynamic fields of interest. So just looking at heat conduction is not enough, but so that's the basic problem we want to understand. Okay, and because it's clear that it's a very extreme example where one would like to test the whether the hydrodynamic limit is valid or not, because there are going to be shocks and very high temperature regions. So this is the idea. Okay, so this problem is very interesting because there's an so the Euler equations, which describe the hydrodynamic fields of density, momentum, and energy in any fluid. So these are the Euler equations, and usually they are of course nonlinear equations which are difficult to solve. But for this particular initial condition of when you have a blast and then you look at long times, it turns out that there is an exact solution which was obtained by Taylor, von Neumann, and Sedov. This is around the time of the atomic bomb, first atom bomb experiments. Okay, so so there's an exact solution, and this is why it's good to investigate this in detail. And so one dimension is even more extreme, because we know that in one dimension you have this phenomenon of anomalous heat transport and violation of Fourier's law. So we just want to understand what happens in this kind of a situation. Okay, so what I'll present is basically a detailed comparison between what you get from Newtonian dynamics, molecular dynamics simulation of a very simple one-dimensional model. It's a hard particle gas, and then compare this, what you get from the simulations, with what you get from Euler equations or Navier-Stokes-Fourier equations. Okay, so yeah, so okay, so again, this is the two descriptions. So if we have Right. So, I mean, so these are kind of like typical non-equilibrium phenomena, water flowing through a pipe or water boiling inside a beaker. And what is useful to describe a way to describe such non-equilibrium systems? So, of course, there's an atomistic description, but then the hydrodynamic description, what it says is that one just considers, one looks at the conserved quantities. So, for a typical Hamiltonian system, the conserved quantities are total number of particles, the total momentum, and total energy in the system. And then what we say is that we assume that the system is in the dynamics case. We assume that the system can be described in a local equilibrium state, so that if you look at small cells, so like in this system that I have here, so one can construct small cells where each cell is in like a local equilibrium state described by the local density, momentum density, and energy density. Okay, and because these are conserved fields, they evolve slowly, and one can describe them by the equations of hydrodynamics. So what are the equations of hydrodynamics? And so in this case, okay, so given the microscopic the variables, which are the position and momentum of each particle. So this is the microscopic description where each particle has a momentum and position. And the way to construct the macroscopic fields is exactly this, right? So we just count how many particles are there in a given box and divide by the length, so that gives the density. And similarly for the momentum and the energy field. So, so this is how one connects the microscopic and macroscopic pictures. And then what we know is that these three fields, they satisfy the hydrodynamic equations, which are either the Euler equations or the Navier-Stokes-Fourier equations. Okay, so so these equations were of course written when they were written down. One did not really care about the microscopic derivation, so they were just written phenomenologically. So these are basically equations of conservation of the three fields. And so the first equation is conservation of particles, this is conservation of momentum, and this is conservation of energy. And this equation has the, okay, so it has two kinds of terms. So there are terms which are, so these red terms are what are usually called dissipative terms, or so these are dissipative or terms, and this is also what I'll call Navier-Stokes-Fourier terms. So this is the usual Navier-Stokes equation coming from shear viscosity, and then there's a thermal conduction term, which is the Fourier term, right? So these red terms are what are known as dissipative or Navier-Stokes-Fourier terms. And if I ignore these terms, then what I have are the Euler equations, right? Okay, so so the Euler equations have some current which consists of a flow part and a pressure part, and so this is the energy current and this is the particle current. Okay, so now in this equation, there's so the fields of interest are density, velocity, and energy, and then on top of that I have a pressure term. And of course, what I know is that the pressure is given by some equilibrium equation of state. So basically there are only three independent fields, and the other fields are known once I know the thermodynamics of the system. Okay, so there I need some information from microscopics in terms of equilibrium equations of state. Okay, and then the other quantities that appear in this equation are this so-called transport coefficients, eta and kappa, which again are known, of course, now we know how to compute them using things like Green-Kubo formulas and so on, using linear response theory. Okay, so again, given a microscopic Hamiltonian, that linear response theory tells us how to compute these coefficients. Okay, so so these are the hydrodynamic equations, and okay, so now the main question that we ask is how good is this hydrodynamic description? So first of all, I want to say is that there is really no rigorous derivation of hydrodynamics starting from Newton's equation, and in fact, this is part of Hilbert's sixth problem, so far unsolved. I just want to say that in a recent paper, we have tried to do a systematic derivation in some sense of hydrodynamic equations using the method of projections. but this is not what I'll talk about today. Okay, so now, okay, so this is the basic question: how accurate is this hydrodynamic description? Now, one specific problem that one expects in one dimension is that, for example, we know that in one dimension you have anomalous heat transport, the thermal conductivity diverges, and in fact, what is known is that since Fourier's law is not valid, it's believed that you can't write the diffusion equation, but this is replaced by effectively some sort of a fractional diffusion equation. Okay, and the heat carriers are not doing a random walk, but doing some sort of a Levy walk. Okay, so this is some studies which, of course, people have been doing for a long time. I mean, since this first paper of Lepri-Levy and Politi, trying to understand heat conduction from a microscopic point of view. And there, of course, one finds that there's like what you expect from hydrodynamics, which is Fourier's law, is not valid, right? But here, what we attempt is in some sense an extension of this question, where we also want to look at all the conserved fields and not just the temperature field, right? Because in this system, you can't really separate the three fields are intricately coupled, and one has to write the full set of equations to get the full picture. Okay, so so this blast wave problem is sort of a classic problem where we want to understand this. So I just want to see the time to right. Okay, so so let me just talk a bit about the history of this blast wave problem, which is actually quite interesting. So this really some of the first work was done at the time of the this Trinity atom bomb explosion in 1945, and there. So here I show a picture of the first atomic bomb explosion, and these are photographs of the blast at different instants of time. I think this is the time scale is like milliseconds, and you can see this blast. There's a very hot region which is expanding. Right. So the question is, so one of the first questions one can ask as a physicist is, how does this length scale grow? Right. How does this? So you can see there's a sharp shock at the edge of the blast, and it's expanding. And the question is, how does it grow with time? Okay. So now, this is something quite, I mean, one can do some very simple dimensional analysis actually to find out how the radius of the shock grows with time. So basically the idea is that this radius should depend probably just on the energy of the explosion. And the other variable that one can think of is the density of the ambient air into which the shock is growing. And of course, the time, right? So these are the natural variables in the system. And then if we just try to pull out a length scale from these basic quantities, you find that one has to have this particular form. Okay, so so the radius grows with time as 2 by d plus 2, where d is the dimension in which we are working. So one can do this analysis in any dimension. Okay, so from this, in particular in 3 dimension, you find that the radius goes with time sub-ballistically. It's quite slow, t to the power 2/5. It's even slower than diffusion. And in fact, this from the data that you can see get from here, you can verify that actually this fits very well to this observed form. Okay, so and in fact, from just from this simple formula, you can try to estimate what was the energy in the blast, and you get some numbers like this, number like this, which actually is quite accurate. Okay, so okay, so this is a basic idea of the blast problem and the history of where it was used. So now, of course, one is interested in more details about the blast, in particular. Okay, so what we see is that so the blast consists of a region of very hot matter, and outside there is some cold gas which is undisturbed, right? So what we now want to know is naturally, I mean, like what can we say about the density profile inside the blast? What about the velocity profile and the temperature profile? Okay, so for this, the natural procedure from hydrodynamics would be to solve the Euler equations for these 3 fields. And this is what Taylor, von Neumann, and Sedov found. And so they actually found the solution at long times. Okay, so they found an exact closed form solution at long times of these equations. Okay, so I'll quickly go through the basic idea of the solution, which is that, so first of all, you know that there's a length scale, which is this. So now I'm doing everything in one dimension. So in one dimension, the radius grows as t to the power 2/3. Okay. So this 2/3, of course, remains one of anomalous transport in one dimensions, where this 2/3 keeps coming all the time. So it's probably related to that 2/3, but here it comes in a somewhat different way. Okay, so there is this length scale, and now what these people realized is that at long times you have some self-similar solution where the density depends on R and T through a scaling. There's a nice scaling form. Okay, so I mean, so if you do some I mean simple dimensional kind of analysis, what you can see is that the density depends on space and time through this scaled variable x by r, and similarly the velocity depends on these variables through this. So the dependence is on position and time is through just this ratio x by r. Okay, so okay, so there are these factors which are not so important, but the main point is that we are now looking for self-similar solutions at long times. And so now what you can do is we can use this, we can plug these scaling forms in the Euler equations, and that would give some equations for these three scaling fields G, V, and Z, right? And then there's a shock front, and from some analysis one can get some conditions on what happens at the shock. There are some jumps which can be determined exactly. So there are some boundary conditions at the shock fronts. Okay, we know the exact position of the shock, and we know the boundary conditions of the shock. And then, of course, the total energy inside the system is conserved. So that's one more condition. So now it turns out that you can actually just solve this equation. So I won't, I think I won't go into the details, but somehow you can solve these equations completely and find exactly these scaling forms G, V, and Z. Okay. So that means we basically know the three density fields at all times. The profiles of the three fields at all times. Okay, so the solution, I mean, basically it comes in this form. The scaling field for the velocity, it satisfies an equation like this, which you can numerically solve. And once you know the velocity scaling field, you can obtain the scaling field for, so V, Z, and so there's G, V, and Z. These are the three scaling fields for the three conserved quantities, right? So first you determine V, and then from that you can find Z, and then from that we can find G. Okay, so so this is the exact solution, and we know the profiles from hydrodynamics, from the Euler equations exactly. Okay, so these are the best references for this for the discussions on this problem: Landau, Lifshitz, Sedov, and Jeldovich, and Reiser. Okay, so now we want to see how does this agree with microscopics. And for this, what we look at is this one-dimensional gas of hard point particles. Okay, now, okay, so this model is basically point particles which just meet and collide elastically. So it's a very simple model. So they move ballistically most of the time, and then they collide elastically. And okay, and then if the particles have all equal masses, then it's a very trivial model. It's almost like a non-interacting system. But there's this so-called alternating mass system where you take the particles to have M1, M2, M1, M2 alternate masses. So then the system is sort of non-integrable, and it has very good thermalizing properties. So that's the system we explored. Okay, so the thermodynamics of the system is still of an ideal gas. But it has very good ergodicity properties and so on. And this is the model we want to simulate microscopically to understand how this shock evolves. Okay, so this is the system. So like I said, there are n particles with position and momentum given by qj and masses mj, and the masses are alternating. Okay, so we want to create the same blast kind of initial condition. So what we do is initially you distribute all the particles uniformly in space, and then you have to choose their velocities, and you choose their velocities. In some small region, you choose their velocities at some corresponding to a Maxwellian distribution at some temperature, while elsewhere you put them at all particles are at rest, right? So it's like zero temperature, and inside there's a hot region. So this is exactly like the blast initial condition, but now at a microscopic description. Okay, and this is the dynamics. Okay, when two particles collide, they just conserve momentum and energy. So their post-collision velocities change in some simple linear equations. Okay, and so this is the initial condition that we started with. So you have some Gaussian initial profile, and then you just run the molecular dynamics okay, so if you just look at the trajectories of the particles, this is what it looks like. So here I plot, so initially every particle is at rest except for the central region out here. And then if you just plot the trajectories of each particle with time, it looks like this. Okay. So out here, it's all cold particles, and these are the inside the blast. Okay. So this is like looking inside the blast. What are the particles doing? Okay, and this dashed line out here is in fact exactly the curve that I had, is this R of t goes as t to the power 2/3. So that's the expectation from hydrodynamics, right? And you can see actually that even the microscopic model for a single realization stays close to the hydrodynamic description. Okay, so now what we do is we construct these three hydrodynamic fields from our microscopic data. So here, okay, so this is, I had already defined how you can start from the microscopic variables and construct the fields. And here there's some averaging, which is with respect to the initial condition. Okay, so that's just to get some smooth data. Okay, so now if you do like heat maps of these three fields, this is what it looks like. So if you look at the temperature, I mean, it's not completely clear, right? I mean, what do you expect? I mean, if you think about it, I mean, it's not clear, but here you see that it's very hot in the center, and then there's some profile. Okay, so at the sides again it's hot, and in between it's a bit colder. Velocity profile inside, it's almost zero velocity, and then there's some peak at the center, and then some at the sides also it's very high velocity at the edges. And sorry, this is the density profile, and then this is the velocity profile. Okay, so now what we want to do is, once we have these profiles, we want to test the how good is the scaling solution of this Taylor, von Neumann, and Sedov. That's let's see how this works. So here I plot these three fields at different times as a function of space. Okay, so at very early times, what you find? Okay, so at time 0, of course, it's uniform. Completely uniform density, but then there was this blast, and then after time t equals to 10 to the power 4, if you look at it, what you find is that at the center it's very low density, and at the edges it's very high density. Okay, so the particles have been pushed to the edges, and at the center there's some low density region. And the velocity field similarly looks like this. So this is at the earliest time, and then this is at later times, and this is the velocity field, and this is the temperature field. Okay, so now what we expect is that this solution should look self-similar, which means that if we scale appropriately, then they should collapse. And this is exactly what we find. If we divide x by t to the power 2/3, which is this scaling variable zeta, then all these different curves, they collapse into this universal curve. And the dashed line that I have here, if you look at it closely, I mean, there's a dashed black line. That is the TVNS, a prediction from Euler equations. Okay, so you can see that in all three fields, the agreement is really quite spectacular, except that okay, at the center of the core of the blast, there's some deviation. Okay, so in particular, the temperature field that is predicted from the Euler equation actually has a divergence at the center, and this is not what you see in the simulation. In the simulation, it's kind of smoothened out. And so at the center, you can see some deviations. Okay, so at the shock front, actually, you can see that at longer times, the prediction gets better. So at the shock front, the solution, the hydrodynamic solution, in fact, works quite well, which is also quite surprising. So the only deviation is at the core of the blast. Okay, so I think I still have some time. Okay, so this is now what we want to understand, like why is there a division at the center? And okay, so perfect agreement between simulations and Euler description except in the blast core. And so now one worries about the terms that we have neglected in the Euler description, right? So there were these dissipation terms from viscosity and thermal conduction. And so the question is, are these important? Okay, so what one can do is one can do a self-consistency check. I mean, so we have solved these equations without the red terms, and we take those solutions and ask, like, if we plug it in these expressions, then how does this term compare with this term? Okay, so so we take the ratio of, let's say, this term and this term using the exact solution that we know from here. Okay, so this is asking, is dissipation important in some region of the system? Okay, so now if we look at this ratio, then what we find, in fact, is that this ratio at different times and space, it has this dependence. Okay, and so there are all these funny powers that arrive, and you might wonder, why do you get these powers? So that's because here we have to assume some form. So this thermal conductivity actually depends, has some dependence on temperature and density in this in our system. And the temperature dependence is T to the power half, and the dependence on density is rho to the power 1/3 based on numerical simulations. And we use that, and that somehow leads to all these funny powers. Okay, so anyway, this is this depends on the some details, but for our case, this is what we get. And now we ask, is this ratio large in some region, right? So what you find is that this R is much greater than 1 if we look at regions in space which scale like this. Okay, so therefore, in this kind of regions in space, these terms start becoming important, and this precisely is the core region. Okay, so the size of the full blast is T to the power 2/3, and so that is, of course, much larger than this power out here. So this is some core region in the blast, right? So there's a overall blast region, and then there's a core region which has this length scale given by this, and in this region we expect that these terms are important, and so we expect a different scaling solution. Okay, so this explains why in the core we see some differences. Okay, so now what we did is we solved now if once you include these terms, there's no exact solution of the equations even at long times. And so then what we do is just numerically solve this PDEs and see what we get. Okay, so now I present numerical solution of the Navier-Stokes-Fourier equations, and these are the solutions. And if you remember the molecular dynamics simulation results, they looked very similar. And again, they have the same scaling collapse. And then what you find is that now you don't have any divergence at the center. In particular in this figure, the temperature, so the dashed line is again the Euler solution, but the hydrodynamic equations with dissipation don't show any divergences. Elsewhere, it continues to be as good as the Euler equations, right? So in the core now we have some differences. So we see that indeed the dissipative terms lead to a better agreement with what one expects physically. Okay, so in this slide, what I do is I compare all the three so we have direct molecular dynamic simulations, we have Euler equations, and then we have the full Navier-Stokes-Fourier equations, and we compare all three of them. And what you find is, so let us just look at the temperature field, let's say. In most of the region, there's a good agreement between all three. But in the core, now we see somewhat better agreement between the Navier-Stokes-Fourier and the microscopic models. At least there's no divergence, unlike what you see in the Euler equation TVNS solution. So, but we still don't get a perfect agreement between microscopics and the hydrodynamic equations. Okay, so there's still some region where things don't work. Okay. So here, I mean, so now what we also did is that we did a more careful, so in the bulk, of course, now we have a different scaling solution than what was, than the self-similar solution that I wrote earlier. And so we can actually, I mean, write down this, the expected solution, and then this again you can try to solve these equations numerically and see what the scaling functions are. So in this case we can't solve the scaling functions analytically, but we can solve them numerically and compare with what we get in the simulations. So yeah, so this agreement is not completely perfect, though the scaling works, but the scaling functions don't match with the simulations. So that is the main conclusion. Okay, so I mean, so this is just one plot where I sort of show. So what I showed is earlier that we did do some averaging of the microscopic evolution. And the averaging was done over many initial conditions. Okay, so now in a real system, of course, you just have one realization, right? You don't have an ensemble. So one question that is of interest is that if you look at a single realization, I mean, do you still get the same result? So in this case, of course, you have to put a large number of particles and do an appropriate coarse graining of over space and all. And what we find is that actually, even for a single realization of this of the microscopic process, you get the same result as you get for doing an ensemble average. Okay, so this is really very satisfactory because I mean, this is what I mean. So the main idea is that coarse graining over some length scales leads to hydrodynamic equations. There's really no ensemble at the that one has in when we look at real systems. Okay, so I think I have finished a bit early because yeah. So earlier I was under the impression that it's 35 minutes talk somehow. Okay, so basically the main idea is that there are what I tried to explain is that there are two descriptions of let's say air in the room, an atomistic description and a continuum description, and how good is that a continuum description is of course an approximation, but how good is this approximation? And we test it in some extreme example, and we find so this blast wave is for this we test this in a one-dimensional case, and what we find is that okay, so there's this model is really nice because there's an exact solution which you can compare with, and the microscopic model is nice because it has the same equilibrium physics as an ideal gas, but it thermalizes quickly. And we find a remarkable agreement between simulations and predictions from Euler. And then we find deviations from the Euler description in the core of the blast, where we understand this is arising from heat conduction which has to be included in the description. Okay, so and the scaling in the core region, so far we don't have an analytic solution. I mean, so this is a bit difficult because this is a system with two, so there's a two scaling regions. There's a core region where you have some scaling, and there's a bulk region where you have a different scaling. And somehow you need to match these two scaling solutions. Using some appropriate mathematical techniques. And this we still have not been able succeeded in doing. So this is kind of an open problem. We still don't have complete agreement between microscopics and macroscopics. And one of the main difficulties is that the transport coefficients in one dimension for this system are not known so accurately. Of course, this is a question, I mean, does anomalous heat transport in some sense require some modification of the hydrodynamic equations? So these are the references. I mean, so there's a long paper and then there's a short paper in the archive, which recently got just a few days back. It's there in this PRL, and there's a related paper actually on trying to derive fluctuating hydrodynamics from again the microscopic description, which is this reference. Okay, so thanks again for your attention, and I'll take any questions.
Thank you very much, Professor Dhar. Now we have some time for questions. Professor Nikolai Nikolaevich Smirnov.
Okay, thank you. Thank you very much. It was very interesting and impressive lecture. I liked the results. But I have one question. Can you show slide number 18? Just I failed to understand one of just your estimates. Is it possible? So there is an estimate of the effect of viscous and heat conductive terms. And
yeah, so this is the estimation, a comparison of the heat.
Can you show it? Can you show it?
Okay, I've already put it. I don't know if you can see it.
Well, we cannot
Maybe
see, but
time.
Nevertheless, there is the comparison of just some ratio between distance and time in the power 38 over 93 or something like that. And so,
right, yeah.
Yes, here it is. And so, just the question is that just the last one. It seemed to me that x and t and r are dimensional values. At least they were obtained within the frame of dimensional analysis. And then this ratio t in the power 38 over 93, somehow it puzzles me, because the dimension is violated and somehow x and t there, or everything is dimensionless here.
Yeah, so there are some factors which make it dimensionless, which I have not included, but of course, finally it's a dimensionless, because the starting number is dimensionless. So R is, I mean, like by definition, I use this ratio with this ratio, they have the same dimension. So this quantity is dimensionless, but I have ignored some factors.
Okay, but in the equations, in the upper equations, x, is it dimensional? You take the derivative over x, and it seems to be dimensional. But then somehow, unexpectedly, 2 lines below, it turns to be dimensionless. So, well, probably a big amount of derivations is missed here, but the result, when you define the region, it is dimensionless. Then it is worth to show how x and t were dimensionalized, because else this estimate is useless, since we do not know which are the real values.
Yeah, so let me just repeat what I said. So if you look at the heat conduction term here, and the term which is derivative of temperature times rho, so they of course have the same dimension because they're on the same equation, and I'm just comparing those two terms. So I'm comparing this with this, So this ratio is definitely dimensionless.
Okay, that's
And
fine. And below, x less than t in the power 38 over 93. This is the main just conclusion of this slide, just the main
right, yeah.
estimate. And so in case x and t are dimensionless, it is worth to show how they are dimensionalized, because else this estimate turns to be useless. This is the statement. It's not the question.
Right, yeah. So I'm saying, like, if you look at our paper, you will find that it is written in dimensionless form. I mean, here I'm just interested in the time and space. So
Okay, I understand, but it's necessary to show how these parameters x and t were dimensionalized, on which values. This is to understand the estimate and to use it for all the listeners. Just to use your results, it's necessary to know. Okay, thank you.
Thank you. Yes, Professor Anton Krivtsov, please.
Professor Dhar, thank you. Thank you very much for your very interesting lecture. And yes, so very interesting lecture. My question is, there is molecular simulation, there is hydrodynamics, and there is another thing in between, kinetic approach. So did you think about considering these three steps and comparing them?
Right. Okay. So yeah. So that of course is one question. So from the Newtonian approach, so one more step is the kinetic, or let's say the Boltzmann equation approach. And from Boltzmann, one can go to hydrodynamics. So kinetic is of course kind of intermediate between hydrodynamic and the microscopic description. So yeah, so I think sometimes, of course, like when the hydrodynamics doesn't work, then one looks at the kinetic description to explain, like especially when you have like low density gases and so on. Then the kinetic description is useful for explaining things which are not completely described by hydrodynamics, I think. But in this case, I think at least it looks like the hydrodynamic description is almost explaining everything already. So I think one doesn't really need the kinetic description.
Sometimes from some points of view, it can be even simpler than hydrodynamics. For example, sometimes it can give linear equations instead of nonlinear, which is usual for hydrodynamics. But this is just a comment. Of course, could be different. Thank you very much.
Thank you. Then the online participants, please, Professor Gavrilov.
I have the following question. At slide 10, I think, I saw that there was a condition of conservation of energy for blast wave. Yes, this condition at the bottom of the slide. Why can we use such a condition? And usually the blast wave is the dissipative structure.
No, but okay. So the total energy inside the blast has to be conserved, right? I mean, so of course there's dissipation, like there is viscosity and thermal conduction, but finally, so what those things do is take energy from like the large scales to small scales, but the total energy, which is has to be conserved, right? I mean, so if you think of the microscopic picture, it's clear that the total energy of, can't, because there's no dissipation mechanism really, like, finally it can only go from like the flow to let's say the temperature field, but on the whole it has to be conserved, right? Because energy, has to be conserved. I don't know if I answered if that was your question then.
Thank you.
Okay, thank you, Professor Wolfgang Müller.
Thank you very much for your stimulating lecture. I particularly like your last equation. That's a fascinating example. I would like to make a comment to your last slide.
Yes, Professor Dhar, if you share screen again, we will be able to see it.
I can see it. I hope the rest in St. Petersburg can see the last slide where he says main difficulty. Just a comment. You know, of course, that the Fourier heat conduction equation is a parabolic one, and it has been modified by Cattaneo and recently by Krivtsov to become a parabolic one. And the same problem arises with the Navier-Stokes. It is also parabolic. So you have this artifact of infinite propagation of disturbances, which are very small on a large scale, but still in principle there. There has been an attempt to modify that by adding a Maxwell term into these Navier-Stokes equations, similar to the Cattaneo term. And I'm just wondering, maybe there is also a way to develop something like the changes Professor Krivtsov did to the heat conduction equation to get to a truly physical understanding of the kinetic, of the momentum transfer in such problems.
Right. Okay. So yeah. So I know this. So of course, yeah. I know about this Cattaneo model where, but at least I don't know how to incorporate it, those kind of descriptions into the standard hydrodynamic equation. So actually, if you know of like work on this,
if you are interested, there are several references where.
Right. Yeah. So I would be interested actually. I mean, in knowing about those references. Right. So right now, I don't know of this, like how you can incorporate those into the standard hydrodynamic equations.
It is possible, and if you like, I can send you the reference.
Yeah, that will be great. I mean, if you can send me those references.
Thank you.
Yeah, thanks.
Thank you very much. Let us thank the speaker again.